Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. Today, we are going to start a new chapter, stochastic process and the stochastic calculus. And the first thing we need to talk about is the fundamental of all the stochastic process, which is the Markov chain. Well, I think it's like one of the most amazing concepts in the whole statistic kingdom. Let's first have a chapter overview. So in this chapter, we are going to cover a few topics: Markov chain, random walk, and martingale, and also dynamic programming, which are often not included in introductory probability courses. They are some kind of advanced level. And unlike basic probability theory, these tools may not be considered to be like a standard requirements for your job, but a good understanding of these topics can simplify your answer to many problems and make your solution much more pretty or much more advanced compared with your compared with other candidates. And once you learn that, you will find many problems turning into fun to solve math puzzles. I listed all the questions here, and I don't know why this part is missing. I don't know why is that. But anyway, you can see we have Markov chain, martingale, and random walk. Today we are going to cover this part because we are going to talk all the topics through and let you fully understand what the Markov chain is. And next lecture, we are going to talk about martingale and dynamic programming. And in the last lecture, we are going to talk about Brownian motion and stochastic calculus. And so far, we have already solved 105 questions out of in total 181 questions of green books. So congratulations for you and also congratulations for myself. We only have like we only have 3 more chapters, and the last chapter is related with coding. So we are just going to go through that. We are going to emphasize more about the coding parts when it comes to our lead code lectures. Okay. So now let's start. What is Markov chain? Before saying that in a more statistical way, I want to say it in a more art student way. So Markov chain is things like all the things related with the future is only related with now. In other words, once the current state is known, the past history has no bearing on the future. It seems a little bit romantic, right? 你的过去与我无关，你的未来只取决于你的现在。Yeah, sounds like a good word you are going to say when you try to please a girl or a boy. Okay, so a Markov chain. Anyway, let's come back to the statistical part. A Markov chain is a sequence of random variables x0, x1, xn with a Markov property that given the present state. So conditional on the present state xn, right? So this is the only one that should be related with us. And if we also have the historical states, the past states, the future states, let's say n plus 1, should be equal to only conditional on the current states. And these I and j from 1 to n represent the state space from 1, which is the first point, and this is the second point. I think this is the first minute, this is the second minute, and this is the nth minute. Okay, things like that. So now the thing we are interested in is the transition probability, which is the probability from state I to state j, which does not depend on n. So we can write a transition matrix composed of all the different transition probabilities, Pij. So for example, in the initial probability Px0, we can have probability Px0 equals to 1, Px0 equal to any value, and then they should be sum equal to 1, okay? And then the probability of a path is that if at the first state, we are at I1, and at the second state, we're at I2, and all the way go ahead, then we can form a path, right? So it's like, this is 1, this is 2, this is 3, let's say we have 3 states. At the first state, you are at A. At the second state, you are at B. And the third state, you are at C. Okay? And then we can also write a transition graph, which is a good way for us to visualize the whole stochastic process. For example, if we already have a transition matrix, let's say like this one. So how do we read this matrix? It means that the probability from it always be I to j, okay? the sequence is always I to J. So this part means if we start from state I and we are going to state J, the probability is 0. So there is no possibility for us to do that. But if we start at state 2 and we are going back to state 1, we have 1/2 probability to do that. And you can see all the way here. And you can see one interesting thing is that each row should be sum equal to 1, okay? Each row should be sum equal to 1. And we are going to tell you that if the column can also sum equal to 1, then this means it is what? It is stationary, okay? It means it is stationary. Anyway, but we can convert it back to a picture like here. So from state 1, we have the probability each of 1/2 to go to state 4 and state 2. And at state 2, we have 1/2 probability to go back to state 1, and another 1/4 probability to go to state 4 or 3. And at state 3, we have 0.4 probability to stay at state 3. And we can also go to state 4 or 2, right? So this is very clear. And now let's come to some advanced topics. So classification of states. So we will call a state J is accessible from state I if there is a direct path in the transition graph from I to J. So, and it states I and J communicate if I is accessible from J and J is accessible from I. So we can go back to the plot here. We can see 2 is accessible from 1, right? But on the same time, 1 is also accessible from 2. So 1 and 2 communicates. You can see there are double directions here. And the next thing is that we can say a state I is recurrent if for every state J that is accessible from I is also accessible from J. It is a stronger definition compared with communicate because it requires every state, okay? So you can see for 1, is it recurrent? No, because 1 can go to 4, but 4 can never go back to 1, right? So 4 does not communicate with 4. And we can see the only one satisfies the recurrent condition is 4 itself, right? Because at 4, you always go back to 4. It communicates with itself. It sounds weird, okay? And if they are not recurrent, then they are transient. Transient means there is a probability, you can think in this way, there is a probability that they are going to eventually leave this state and never come back. You see all those Markov Chain properties, if you link it with fall in love or 谈恋爱, right? You can see a lot of interesting patterns. You know, I love her, but there is a probability that she could leave and never come back. But it's not the same probability for me. That it's not equal between us. Yeah. Anyway, just some funny joke. And we also have absorbing Markov chain. A state I is called absorbing if it is impossible to leave this state. It is something like what? Like marriage in ancient time, right? You can never leave it. You cannot have a divorce in ancient times. So it is something like absorbing. Okay. So classification of states, now we are going to have 2 important formulas which are going to help us solve all the questions below. The first one is for absorbing probabilities. To reach a specific absorbing state, we can denote this state as AS equal to 1, and all other absorbing states will be denoted as 0. And we can write all the equations for other transient states. Please notice that for I, it is actually Pij. So from I to J and multiplied by Aj, not Ai, okay? Multiplied by Aj, and it will be the same for the equation for the expected time to absorbing. And this is easily derived with the law of total probability by conditioning the absorbing probability on the next state, okay? And it will be the same for the expected time. The only difference is that we should plus 1. Because each time once we go to the next state, we are going to expand 1 step, right? We are going to use 1 more step to go to the next state, okay? Since it takes 1 step to reach the next state. And now let's come to the problems. The most classic problem related with Markov chain is the gambler's ruin problem. So player M has $1 and player N has $2. So each game gives the winner one from the other. And as a better player, M wins 2/3 of the game, and they play until one of them is bankrupt. What is the probability that M wins? So as long as you identify there could be some absorbing states, you can solve the question easily using the two equations here. So this time we are asking the probability. So it is related with the equation for absorbing probability, right? Now, first we want to find the specific absorbing state we want. The state is that M wins, right? M wins means that the dollar M should equal to 3, right? M equal to 3. And what's the probability that M could reach 3? So anyway, we can first denote this A3 as 1, okay? And then another observing state is what? A0, right? Then it should be 0. And we can have what? And we can have, sorry, it's my Siri. So we can have A1 should be equal to sum according to the formula here. Okay, according to the formula here. This should be J equal to 0 all the way to 3 and P1J, AJ, right? And we know we are starting from A1 where M has $1, right? And the probability P10 is what? Is 1/3, right? And A0 equal to 0. So we can have this is 1/3 multiplied by 0 plus 2/3, which is going from 1 to 2. And we have 2/3 probability because it is the case that M is going to win the first round, right? And he is going to have A2, right? And is it possible to go directly from 1 to 3? Not possible, right? So it is already the total probability here because the sum of all the probability is equal to 1. And we also have A2 is going to be what? It's going to be 1/3 to A1 and plus 2/3 to A3, which is equal to 1, right? And combining these two solutions, we can have what? We can solve A1 equal to 4/7 and A2 equal to 6/7. And this is the probability that M wins is A1 because we are starting from M1, right? And it is 4/7, which is larger than 1/2. So should M play this game? Of course, he should. And you can see M, since it has less gamblers, has less dollars, initial money. So he should only get involved in this game when it has the better odds to win, right? It is logically reasonable. And now let's come to the next question, which is the dice question. So two players bet on rolls of total of 2 standard 6-face dice, and player A bets that the sum of 12 will occur first, and player B bets that 2 consecutive 7s will occur first. And the players keep rolling the dice and record the sums until one player wins. What is the probability that A will win? So again, of course, you can solve this problem by conditional probabilities, but it is very complex, especially during an interview stage. You are going to become nervous. But let's do it using the Markov chain, which is going to be intuitively appealing, okay? So the key state is still to have the absorbing state. While absorbing the state, A will win, right? The state, we want the probability that A will win. A wins, that 12 will come first. So we define A12 equal to 1. And then another absorbing state is what? A7 is going to be 0, right? And let's find the initial stage S. Initial stage S. Let's denote it with S, okay? Then we can have what? AS is going to be, so if it gives us a 7, which is a probability, which has a probability of what? How many 7s? If we want a 7, how many combinations can there be? 1, 6, 2, 5, and 3, 4, and the reverse of all these three, right? So in total, there are 6 of them. So there are 6 over 36 probability that we can go to A7, where the first 7 comes out, and plus what? Plus, if directly there is a 12 coming, which is 1 over 16 multiplied by 1, right? And there are all the leftover states, 29 over 66 multiplied by AS itself, right? Then also we can have when we have the A7. What's the probability from A7 to A77, double 7? Then it is 6 over 36. And this is going to multiply by 0 because A double 7 is 0. And plus, we have 1 over 16's probability to directly go to A12, which is also 1. And we have another 29 over 36 probability to reduce to the initial state. And to double check, we can have the sum of these 3 equal to 1. And also the sum of these 3 also equal to 1. So perfect. Now we just need to solve this equation. And we can have what? We can have AS equal to 7 over 13. Okay? You see, as long as you know this Markov chain formula and you know how to construct the problem by defining the absorbing states and list out all the equations you need, it will be quite easy for you to solve this kind of question. And now, let's go to the next one, which is coin travelers. This is a complex problem. Let's go for the 3 parts one by one, okay? So the part A, if you keep on tossing a fair coin, what is the expected number of tosses such that you can have triple heads in a row? What is the expected number of tosses to have tail plus double heads in a row? So again, we can using the same, this time we are calculating the expected number. So we are going to use what? We are going to use the equation for the expected time of 2 absorbing. This part is similar to this part, but the only thing you should remember is that do not forget this 1, okay? So let's first find triple heads. The triple heads that also we define the S as the initial stage, okay? I'm not going to repeat this again. We just is going to use S as the initial stage. So for US, it is going to be 1. First, we write 1, okay? 1 plus what? 1 over 2, and it will be reduced to US if they toss the tail, and plus 1 over 2 to have what? UH, right? The first edge. And we can also have UH equal to what? 1 plus 1 over 2, it will reduce to US, always the case. Another 1 over 2 to have UHH. And UHH is going to be 1. Oh, by the way, we are going to have UHH equal to 1. Right? This is going to be again 1 plus 1 over 2 US plus 1 over 2 UHH. Oh, so sorry, this part should be 0 because this time it is the expected number. So if we already at triple H state, then how many steps, how many tosses do we further need to get into triple H? 0, right? Because we are already there. And by combining these 3 equations together, because this is 0, and then we can solve the problem to be US equal to 14. Okay, it is going to be quite easy. And what's the expected number of tosses to have tail HH? Again, this time we just need to change a little bit about the solution. So let's cancel out this part, okay? So now what's the expected number of tosses to have tail HH? Again, we have the initial stage, which is going to be 1 plus 1 over 2. If the H, then it reduced to the original state, right? And if it is tail, then we have UT. And how about UT? UT have 1 plus 1 over 2. This time we will not go, if we toss the tail, then it will not bring us to the initial state, but stay at UT state, right? And if we got the hand, then we move one step forward, which is tail edge. And the mu tail edge is going to be 1 plus 1. 1 over 2 ut plus 1 over 2 uth, which this part is going to be 0. And combining these three, we're going to have us equal to 8. Okay? Again, we just need to use the formula to solve this kind of question. Quite easy. And then how about part B? Keep flipping a fair coin until either triple head or tail HH occurs in the sequence. What is the probability that you will get an HHH sequence before THH? So this time, how should we define the problem, right? Again, we are asking the probability, so we should go back to use the first formula. So we're going to have, if we want a HHH beforehand, then AHHH should be 1, okay? And then ATHH should be 0, right? And then again, we're starting from the initial stage. It should be 1 over 2 to AT plus 1 over 2 AH. This time we will never come back to the initial stage because we have either T as the first one or H as the first one, right? And then we have AT is going to be 1 over 2 AT plus 1 over 2 ATH. And AH is going to be 1 over 2 AT plus 1 over 2 AHH. And how about ATH? ATH is going to be 1 over 2 AT plus 1 over 2. If it is THH, then it should be 0. So this is canceled out. And then we also have AHH equal to 1 over 2 AT, if it is T, and plus 1 over 2 A triple H, which is 1, which is just 1 over 2. Okay. Now let's try to solve this one. Because this one is complex, so I'm going to solve that step by step. So from here, we can find what? AT equal to ATH. Okay. And but here we also have what? We also have ATH equal to 1 over 2 AT. So we can have what? ATH equal to 0 and AT equal to 0. Do not panic, okay? So this is quite common, okay? It could be 0. And once we have both is 0, we can have what? We can have AHH equal to 1 over 2 and sorry for that. And then let's continue. So we have AHH equal to 1 over 2. And then by putting AHH here, and this is 0, so we can have AH equal to 1 over 4 and AS equal to 1 over 8, right? So the probability that we end up with 888 is 1 over 8, okay? And now let's come to the part C. Let's add more fun to this traveler game. Instead of fixed travelet for the first 2 players, the new game allows both to choose their own patterns. So player 1 chooses the treble first and announce it, and then player 2 can choose a different pattern. And the player again tosses the coins until one of the 2 triplet sequence appears. And the player who's chosen triplet appears first is going to win the game. So if both of them are perfectly rational and both want to maximize their probability of winning, would you go first or go second? So if let's guess the answer, who should you choose? From the previous part, we know that we should choose the second player, right? Because THH seems to have a better odds than HHH. But why it is the case? Why should we choose the second player? A common misconception is that there is always a better sequence that beats the other sequence. This is wrong, okay? The point is that we can always choose a sequence player two, okay, player two can always choose a sequence where the second and third pattern is the same as the first two of player one. What does this mean? So if player one, let's say we choose edge, 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 then according to the previous problem, player two can choose T, edge, edge. And if it choose T, edge, T, then what can we do? Then we can choose T, T, edge. So these two are the same as these two. And these two are the same as these two. So why it is the case? Why it is the case? A simple idea is that if player one fails during the middle, it is going to bring him back to the original stage, right? But for player two, since we only put the last two patterns here, and it could be possible for it to only reduce to state one. And every time when player one has already have two sequences, let's say he already have edge, edge, there is a probability that player two already finished the game. He already formed out all the puzzles. Okay, so that gives player two a better odds. I think it is an intuitive way to understand why player two has a better chance to win. Because each time when player one only have the first two patterns, player two could already have the triplet. Okay. And so this is going to be all for today's lecture. Hope you enjoyed that. And we are going to see you in the next lecture where we are going to talk about martingale and the dynamic programming. Thank you for watching.